So when we are thinking about the roots of a quadratic equation, right? In essence, what we are looking for are what are the solutions, okay? So usually we are talking about the x-intercepts, right, as our solutions, but I could also ask you for the solutions for a particular y value, okay? And depending on the type of equation we're giving, we have three very distinct possibilities, okay? We're either going to get two real solutions, we're going to get two equal solutions, in other words, the solutions will have the same value, and the third is that we will get no solutions, okay? And this is that part of the mathematics where they gave you a quadratic and asked you to find the values for k where the graph might have solutions or not, okay?
Oh yeah, b squared minus 4ac, that part.
So the discriminant. But before we think about the discriminant, I'm going to write down the quadratic formula for you here, and we're going to analyze it in a little bit of detail to see exactly why this part of the quadratic formula is so useful in helping us find these values, okay? So if we, for instance, take the quadratic formula, which is Keanu's favorite, okay? He can recite it to you probably backwards if you asked him.
I think you mean everybody's favorite.
How is it everybody's favorite? Okay, x is equal to minus b plus or minus the square root of b squared minus 4ac all over, oh, sorry, not all over, add on all over 2a, okay? So if any of you are wondering how this is derived, it's derived by taking the standard formula for a quadratic equation, which is y equal to ax squared plus bx plus c. In other words, a, b, and c are just the constants that could be in front of x squared, in front of x, or alone without an independent term, okay? And by making this equation equal to 0 and quite simply completing the square, and we will get this quadratic formula, okay? So the part of the formula I want to highlight is this part here underneath the square root sign, okay? I'm going to actually include the plus and minus because you guys have learned now that when we take the square root of something, two negative numbers multiplied together or two positive multiplied together will give you the same, can give you the same solution, okay? That's why we have plus or minus, okay? So the discriminant, okay, is this part under the square root, okay? It's this b squared minus 4ac, okay? And just from it being under the square root, right, it can, because of its nature, identify not what the roots are going to be, but what kind of roots we might get, okay? So if you imagine, all right, that b squared minus 4ac, if it's a positive number, okay, that means it will have actual solutions, right? Which means when you're solving your quadratic formula, right, x equal to something, you will actually get numbers out. And because you have plus and minus to deal with, it automatically tells you that you will get two solutions out, right? If we imagine our discriminant being equal to 0, right, we will technically still get two solutions. We will get plus 0 and minus 0, except plus and minus 0 happen to be the same number. Therefore, both your solutions will be exactly the same. Right? We're going to look at this we'll write this down in a second. And finally, if you imagine that discriminant under the square root, b squared minus 4ac, if that ends up being negative, right, you will have a negative number under the square root, okay? And we haven't learned how to deal with negative roots yet, okay? They are out of the real set of numbers. They live in the imaginary set of numbers, which we will look at next year, okay? So for now, if you imagine we get a negative number under that solution, that square root, you will not be able to get any solutions because the formula will be undefined for those values. Okay. So what I thought we would do is, why don't we have a quick look at what's going on here when we're talking about what values of A can cause a graph to be positive, negative, or have solutions, one solution, no solutions. Okay. So here I have a quadratic, right? The quadratic is x minus 2 squared, right? And I've added in this constant plus a, right? So you would have, in your textbooks, they always gave you k. They liked the letter k for some reason, okay? I've used the letter a for this one. So if you have a look at a, right, when they're asking you for the set of values where something might either have roots, have the same roots, or no roots, right, what they're asking you is, for what values of this constant a would that happen? So I'm just going to move the graph around a little bit, and you can see what's going to happen. If I had to decrease the value of a, all right, at the moment you can see at the value of a,
again, that makes it an inequality, right?
we're going to get, well, we might get an equality, not always, okay? Let's just have a look at this first example, right? I've got a equal to 0, and you can see, if I asked you to tell me how many solutions this graph has, you can quite clearly see that we have one solution, right? It happens to be at the turning point of this parabola, right? And it's not actually one solution, it's two solutions that just have exactly the same value, okay? If I had to decrease the value for a, all right, what's going to happen? Well, the graph's going to move down. And because the graph is moving down, right, I now actually get two distinct different solutions, right? So you can visually see that for any value less than 0 on this graph, I will get two solutions. And I can keep moving the graph down to infinity, and I will just keep getting more solutions, okay? If a was 0, you can clearly see that I'm only going to get two equal solutions. Okay? And finally, if I had to take a value for a that was greater than 0, right, not equal to, greater than 0, you can see what's going to happen is the graph's going to move up away from the x-axis. And you can see that we aren't going to get any solutions. Because remember, the solutions are where the graph is equal to, well, in our case, where the graph is equal to 0. Okay? So you can visually see here, for any value that a is greater than 0, we are not going to get any solutions. Okay, so why don't we do this mathematically? Okay, you can visually see now, you've visually seen that at a equal to 0, we will get two equal solutions. For any value less than 0, we will get two very real solutions. And for any value greater than a, or greater than 0, we will get, well, you can see, we're not going to get any solutions. There is no part of that graph that is going to intersect the x-axis, because you can see it's running away, right? Clearly, it's not friends with the x-axis. So let's take our equation and let's look at the discriminant and see what's going on here. Okay, so I'm going to pop back to, so here is our equation. Okay, I'm going to pop it here. It was x minus 2 squared plus a. Okay, now I have this in completed square format, and in order to use the discriminant, we need to write it into this format over here, y equal to ax squared plus bx plus c. Right, so that's just a very simple job of just quickly expanding this out. I'm going to get x squared minus 4x plus 4 plus a, right? So in order to use the discriminant, we need to know what are a, what are b, and what are c, okay? A is just the coefficient in front of x squared. B is just the coefficient including the sign in front of the x term, and c is just anything that's a constant. Now this 4 and this a, they are both c because they are both unaffected by either x squared or x. Okay? We're going to look at some examples later where you might have to factorize out, right, your a, b, and your c. Right? So let's have a look at these two things, right, individually. So if I want real roots, right, I want two real roots, right? If we go back to our quadratic formula, we can see if we want real roots, that means we have to have something inside that square root that's bigger than 0, okay? Because if it's equal to 0, we're just going to get two equal roots, but we want real roots, right? And if we went back to the graph where we were moving it around, you could clearly see that that happened when that b squared minus 4ac must be greater than 0. So we're going to do exactly that. For real roots, we're going to say this discriminant b squared minus 4ac must be greater than 0. So let us quickly make it greater than 0 and see what happens. So b squared in this example is going to be minus 4 squared. Take away minus 4a is just 1, and c is 4 plus a, right? And that must be greater than 0. So we're going to get 16 over here. We're going to get minus 8 and minus 4a greater than 0. If we simplify these up, we're going to get 8, and we can move the 4a to the other side. And I've done something very silly, haven't I? Come on, Kiana. What's 4 times 4?
16. Oh my word. I didn't even see that either.
It's too early in the morning. Okay. And so you can see a must be less than 0. Okay? Which is
in my defense, Mr. James, I haven't had a coffee yet.
Fair. So you can clearly see that for values less than 0, right? And if we go back to our graph, right? For any value less than 0, you can see that we get two very distinct solutions at any point, right, underneath 0. Right, let's go back to if we want to find equal solutions. Okay? Two equal roots. Right? We want b squared minus 4ac to be equal to 0. So again, we're going to have the same discriminant, right? Except this time we're just going to get 16, take away 16 minus 4a. Instead of greater than or equal to, it will just be equal to 0. And so we will get a equal to 0. Okay. And if we have to put that into the opposite one, right, where we want it to be less than 0, we will get a greater than 0. And that will be for roots that are non-real roots, right? We just haven't done, there are actually solutions to those equations. They just don't exist in the real number world. Okay, that's where b squared minus 4ac is less than 0. Okay, so what I'd like to do is actually using an example. So what we're going to do is we're going to go back to our graph and we're going to pick a number for a. Right, let's pick the number 4. Okay, we can clearly see that there are no real roots. Right, now let's look at what would happen when we solved this. Okay, if we were trying to find solutions, let's look at the discriminant and see why we don't get any roots. Okay, what's happening to it for that case? So if we think of our graph, it's x minus 2 squared, and we said let's make it x minus 2 squared plus 4. Okay. So expanding this out, we're going to get x squared minus 4x plus 4 plus 4. So there's my equation, and now I say find me the solutions to this graph. Okay, and you try to factorize that and you can't do it, and you try to complete the square and you scratch your head. So you're like, okay, let's revert to the formula. Well, let's see why we're not getting any solutions. Okay, so using the formula, x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Let's plug in our values for a, which is just 1, b, which is minus 4, c, which is 8, and let's see what is going to happen. So we're going to get minus 4 on the outside, which is unaffected by anything. And inside here, we now have the discriminant, right? This is that magical discriminant part. So we have minus 4 squared minus 4 times 1.
Make 16 minus 32, it will just not work.
Over 2 times 1. Okay, yeah, so it's going to get minus 4 plus or minus the square root of 16 minus 32. So 16 minus 32 is negative something.
You can't do it. It's not allowed. It's against the mathematical laws. We'll go to jail.
Oopsie. So I'm just going to put this over 2 here. Okay. So this is why, if you look at the value inside the bracket, or sorry, underneath the radical, the square root, this is why we don't get any solutions. Okay, because we are trying to square a negative number which doesn't exist in our set of numbers that we've learned so far. Okay, and so we can use that information and that knowledge to our advantage, and we can say, well, for what is under the discriminant? Well, the only values that are under the discriminant are b squared minus 4ac. And so if we want to find the values where we might have or might not have any solutions, we can ask ourselves, well, let's make the discriminant equal to something and see what we get. Okay? So this is obviously quite a powerful tool, and as you can now visually see, this is all that they're asking you to find. Saying for what values of this letter, and they like to use k, would this happen? And in essence, all you are doing is you're just finding a set of values for where the graph might either intersect, only at one point, or not at all. Okay. How's everybody coping with that? Is it nice to see that visually?
Yeah.
Yes.
Yeah, rather than just being told what's going on, now you've actually seen what's going. That's exactly what you're busy doing when you're solving for, well, they like to use k, don't they? Solve for k. Okay. Now k could have been anywhere. I could have put that variable anywhere. In fact, what I can quickly do is, let's quickly go back to Desmos. If you have a look at this equation here, okay, you'll notice I have k everywhere. There's a k in A, there's a k in B, and there's a k in C, right? And at the value where k is equal to exactly a half, you can see that we have just one solution. Okay, and I wonder how, well, I wonder if you guys can tell me, how do you think I knew to put in 0.5 to give me only one solution? Well, let's go and do it. Okay, let's go, and before I move this graph up and down, right, I knew exactly what value to put in there to show you that we'll have two equal solutions here. So what we can do is we can actually take this equation and let's go and work it out for ourselves. Okay. So if you are wondering where I got this from, it's from your textbook. It's exercise 1H, question 5D is the one that we're busy doing. Okay. So it says we have this, we have this equation, k x squared plus 2k minus 1 plus k equal to 0. Okay, and they want us to find the value where we have two. Well, in the question they asked for two distinct roots, but I want to find the part where there were two equal roots. Okay, so Toya, what can you tell me about the discriminant if I want two equal roots? Right, I want the roots to be exactly the same. What would the discriminant have to be?
0.
Yeah, if we go back to the discriminant, we look at it. If I want exactly the same two answers, then I want plus 0 and minus 0. I just want that thing under the square root to be equal to nothing. Okay, because then I will get only one solution. So in other words, I want b squared minus 4ac to be equal to 0. Okay, now all I need to do is work out what a, b, and c are. Here's a. This whole thing is b. And there's c. Okay, so now I'm just going to make the discriminant equal to 0. So I'm going to have 2k minus 1, and this is all squared, including that 2, minus 4 times 1. C is just k, and we want this, equal to 0. Okay, expanding that bracket out, that 2 is going to become a 4, right? We're going to get k squared minus 2k plus 1 inside the bracket. And over here, we're going to get minus 4k equal to 0. We can sort that out. And you can see that we're going to get a quadratic. Right, so let's tidy this up. We have 4k squared minus 12k plus 4 equal to 0. What can I do to make it easier to solve this, Dominic?
Factorize the k out.
I can do something even easier.
Just solve for k because it's a quadratic in itself. K just replaces x.
Okay, and oh, I've left something important out, guys. Come on, who can spot it? What have I made 4ac? I've made it 4 times 1, but it's not 1, it's actually a is also k. That makes a bit more sense.
So then it's just
This is going to be minus 4k squared. Okay.
so minus 8k equals minus 4.
So these 4k squared are
0.2,
fortunately,
means
they're
0.5.
going to get rid of each other. Okay, so we're going to get minus 8k plus 4 equal to 0. And you can see that k will just be equal to a half, okay, which is what we wanted. So if we go back to our graph, that's how I knew exactly to plug in a value of a half. Okay? But now let's have a look. If I change the value for k, all right, I could solve this algebraically. I could say, well, if I want real solutions, right, what must I do to the value k? And I wonder if any of you can guess. Do you think I'm going to get real solutions if k is bigger than a half or less than a half?
If it's less than a half.
Okay, so let's make them less than a half and see what happens. And there you can see, okay?
Oh my.
As k gets less than, now I want to show you something interesting, obviously. If you imagine if we make k equal to 0, what are we going to get?
A straight line.
Yeah, we're going to get a straight line. Okay, so if I made k equal to exactly a 0, you can see we're actually going to get the line x equal to
X equal to minus y.
sorry, y equal to minus 2x.
Oh, yeah, y equal to minus x.
Okay. And as we continue decreasing the value, we will continue getting two solutions. So any value less than a half, and we will get two real solutions. Right, let's go back to our x equal to a half. Okay, here we had one solution, which we worked out algebraically. Now let's see what happens when we take values of greater than a half. You can see that the parabola moves away. All right, at some point it starts decreasing the amount that it moves away, right? But you can clearly see we have no solutions when k would be greater than a half. Okay? And again, we could work this all out algebraically if we wanted to. So instead of making the discriminant equal to 0, if I wanted for real solutions, I would make the discriminant greater than 0. And all that would happen is at this step over here, I would get minus 8k plus 4 greater than 0. Okay? I would move that over to the other side. I would get 8k, and I'll get k must be less than a half, which is exactly what you saw visually. When we made k less than a half, it gave us real solutions. And in exactly the same sense, we could take this thing and we could say at this point, if I want no solutions, minus 8k plus 4 must be less than 0. Again, I'll move that over to the other side. I'll get 8k, except this time it's greater, and I'll get k must be greater than a half. And you saw when I made k bigger than a half, we ended up getting no solutions. Everybody happy with that?
Yep.
Okay, now let's go back to our quadratic here. Right? And another interesting topic that we want to think about is the number of solutions, all right, or the number of roots of intersection between a quadratic, and in our case we'll be just looking at a line. Okay, later on we will look at examples of more complicated things, but for now we're just going to look at the solutions of these two, right? Because they create they are very unique, because we can once again use this discriminant idea. Now, who can tell me what are the roots of intersection? What is this whole thing that I'm talking about? If I asked you for the roots between a line and a quadratic, what are those points of intersection? What can you tell me about the two equations?
They're equal to each other.
Yeah, they're equal to each other. In order to be intersecting, right, at those exact points, those two equations happen to be equal to each other. So if we go to our friend Desmos again, and I throw in a straight line for you, how many points of intersection do you think there are for these two equations? That's looking awfully like a tangent, isn't it? And a tangent has how many points of intersection on a line? Just one. Okay, just one. Okay, so let's assume for the moment that we don't have this equation at the top. It's not x squared something something plus a. Say I've given you the equation for the quadratic as that a equal to 0. And I want you to tell me for what values of b, because now we're looking at the straight line, and you'll notice I have a variable in the straight line as well. And this time I say, well, for what values of b will I either have, well, 2 distinct points of intersection, 1 point of intersection, in other words, a tangent, or alternatively, no points of intersection. And basically all I'm saying is, for any value, if I change the value of b, you can see b is just the constant, right? If I change the value of b, I'm just going to be moving my straight line up and down. So if I move my straight line up and down, this is visually what's going to happen, right? If I move the line down, oh, sorry, you can see that we've gone from having no points of intersection to having, I'm making this confusing by having this as a, sorry, this is supposed to be a plus b. There we go, this will work better now, okay? So if I go back to my tangent over there, if I make the value of b smaller than 5, you can see that the line moves away from the parabola, and you can visually see there is no way we are going to get any solutions to this quadratic. Or sorry, there's not going to be any points of intersection between this straight line and this quadratic. So why don't we algebraically go and see why that's happening? Okay. So we have the line for the equation for the quadratic as x minus 2 squared, and for the straight line we've decided to take the value where y is equal to 2x minus 6. Okay. So Dominic, where are the points of intersection? This is when the two lines are
Equal.
okay. We have y equal to something and y equal to something. That means these things must be equal to each other. Okay. So we make the two equations equal to each other, and we are going to we're going to just try to solve for x. We're trying to find the points of intersection. So usually we try to find the x coordinates first. We're going to get minus 6x. That's going to become plus 10 equal to 0. Okay. We try to factorize. We try to complete the square. It doesn't work. Let's use the quadratic formula and see why we are not getting any solutions. So we have x equal to minus b plus or minus the square root of b squared minus 4ac over 2a. Our a is just 1, our b is negative 6, and our c is 10. Let's put the numbers in and see why we're not getting any solutions. So minus b is just going to become minus 6, which is just 6, plus or minus the square root, right? We're going to get b squared is minus 6 squared, which is 36, minus 4 times 10 times 1, which is just minus 40, all over 2. And you can clearly see that in the discriminant here, we're going to end up with minus 4. Okay, so we're going to have no solutions, right? So in other words, there's no value for x where these two will ever be equal to each other. And visually, you can clearly see why. I mean, the two graphs don't go anywhere near each other. They will never go near each other, okay? And again, because we have made these two equations equal to each other, right, we are just solving exactly like we did for the real roots. We're just trying to, the roots in this case are just the points of intersection. And again, if I change the value for b back to 5, you can see that I get one solution. So if I had to put, instead of having minus 6, right, why don't we do off to the side here? Let's imagine in this case we have x minus 2 squared equal to 2x minus 5. That's the one where we visually saw that we had one solution. Let's see what the discriminant becomes, all right? So we're going to get x squared minus 4x plus 4 equal to 2x minus 5 this time. Minus 6x, and this time we're going to get plus 9 equal to 0. Let's take our x equal to minus b. So we're going to get 6 plus or minus the square root of 36 minus 4 times 9 is 36 all over 2a. You can see that the discriminant this time is going to become 0. And that's where you're going to get plus or minus the square root of 0, which just happens to be the same thing, right? And we'll get 3 as our solution. So if we go back to our graph, you can see that the point of intersection is clearly at the value where x is equal to 3. Okay? And in the same sense, if I had to increase the values of b to greater than -5, you can see that we start to get two very distinct solutions. Okay, two very distinct points of intersection over there. Okay, so if we take this example here where I've made b equal to -4, okay, we can go back again and we can plug in -4, and you'll see that's exactly what we're going to get. 2x minus 4. So here we will have x squared minus 4x plus 4 equal to 2x minus 4. If we run out of time, just quickly log in just so I can give you your homework. Okay, we'll get x squared minus 6x, right, plus 8 equal to 0. Now I could factorize to solve this, but I'd like to use the discriminant just to show you again what's happening. X is equal to plus 6 plus or minus the square root of 36. Right, this time we're going to get minus 4. So anyways, getting back to our solution here, you can see clearly that this time the discriminant is going to be equal to 4, which is a very nice number. You get plus or minus 2, which gives us our two very distinct, right? We're going to get 6 plus 2 over 2 or 6 minus 2 over 2, which is going to give me 4 or 2. Okay, and if we go back to our graph for a second, you can clearly see at x equal to 2, I have a point of an intersection, and at x equal to 4, I have a point of intersection. Okay, and again, we're using this and saying that, well, if I want to find all the possible solutions, right, well, I can just make that discriminant either greater than 0, because then it will give me all the real solutions. I can make it equal to 0 if I want just one solution, and I can make it less than 0 if I don't want any solutions, okay? And it would have basically given you that any value for -5 would give you one solution, any value for less than 5 would have given you no solutions, and any value greater than -5 would have given you two real solutions. So I hope that helps to make more sense of what you're actually solving when you're looking at the discriminant. Okay, you're just looking for either the two roots or the two points of intersection, which range of values. If you weren't given an exact number, if you were given a variable like this k and said for which values of this number would you get these different types of solutions.